Hello there. This is video number 3 of section 4.3. And here I just want to go over sort of something that ties together partly what we learned, I think it was section 4.2, and the sort of main idea that we introduced this section, which was bases. So we had, sort of learned about these two subspaces which arise from looking at a matrix, the column space and the null space of a matrix. And so what I want to do here is show you how you can actually find bases for each of these subspaces. And it turns out that the algorithm for doing so is remarkably similar. In fact, it's basically the same from matrix to matrix. And so I think the easiest way to learn how to do this is just to work through an example. So here we've got a 3x4 matrix. And so if you remember, that means that the column space of this matrix is a subspace of R3, right? Because remember, the column space of a matrix is just the set of all linear combinations of the columns of the matrix, or just the span of these 4 columns. And so if you're already thinking back, we sort of have already talked about being able to find a basis for the span of a set of vectors. So as we'll see, this problem will actually relate a lot to the example we ended with last video. And then remember, the null space is a subspace of R4, because remember, this is the set of all vectors that are solutions to the homogeneous equation AX equals 0. Right, so remember, the null space is all of those vectors, right? And so if we're multiplying by a vector x, if you imagine lining it up, it would have to have dimension 4. So we're just going to go through how to find each of these. So we want a basis for the column space and a basis for the null space. So if you remember from last video, we had the last example we ended with was being given a set of 4 vectors in R3 and being asked to find a basis for the set spanned by those vectors. And so notice here, the column space of A is actually just defined to be the span of these 4 vectors. And so now I didn't intentionally pick, I actually did not intentionally pick this to be the same, 4 vectors of length 3, and so certainly this does apply to other numbers. But so notice I forgot to write span. Okay, so do that. Column A is equal to the span of this set. All right, so notice here each vector I'm adding is just a different column of A. All right, so we know how to find a basis for this set, right? Assuming the set isn't already a basis, which we actually know it's not, right? Because there are 4 vectors of length 3. So this set cannot be linearly independent. So we can actually just apply the same method that we applied at the end of last video. So what we do is, of course, we now go back to the matrix A. And so if you remember, the way we were able to find this basis is by recognizing that if I row reduce this matrix, remember each variable in the row reduced matrix corresponds to 1 vector, right? So column, in the row reduced matrix corresponds to 1 vector. And so for that reason, if you think back to it as sort of a system of equations, basically each row that corresponds to a pivot represents, you can say, like a linearly independent vector or so, and column that corresponds to a pivot will represent a linearly independent vector. and each column that doesn't will sort of be something that's redundant, right? Like it's sort of a free variable, and so we can write that in terms of the other vectors. So row reducing this. And so at this point in the course, I'll probably start actually doing full row reductions less, partly because, you know, we're often going to be row reducing sort of in conjunction while learning something else new. And so oftentimes row reducing will end up, the amount of time it would take up starts to become sort of not worth doing it. So certainly if you have any questions about the row reducing steps, I'm happy to answer them. But at this point, it's sort of assumed that we're all comfortable with row reducing, and that, you know, so there'll be times where I still do it when we introduce new things. But for now, if you row reduce this, you get the following matrix. And so the way we interpret this, so notice if you think about this as a system of equations, right? We've got two free variables, x3 and x4. And so if you'll remember, right, each one of these variables corresponds to coefficients from a vector, right? So this vector in the original system of equations would represent all of the coefficients of x1, x2, x3, and x4. And sort of the way you can think about this is that, like, the two free variables we get will always correspond to the linearly dependent vectors in that way. But so what we do know is that the columns that correspond to leading ones, or pivots, whichever you prefer, are the columns which can give me a basis for the column space of A. So these two columns correspond to the first two vectors. And so we actually know that a basis for the column space of A is given by the set 2, 2, 3, and 4, negative 6, 8. And so we could say that span of, other way around, that the column space of A is equal to the span of this set. So much like we did at the end of last video, we can find a basis for the column space of A by row reducing A, looking at the variables that correspond to pivots or leading one, or in this case, maybe if you prefer the columns of A, which correspond to pivots or leading ones, and then taking those same two indexed column vectors from the original matrix A to get a basis. So that's column space of A. How do we find a basis for the null space of A? So I also claim, actually, that while we haven't maybe mentioned it quite as clearly as the column space problem, we have found bases for null spaces of matrices before. So to do this, well, we want to express the solution to AX equals 0 in parametric vector form. So remember, to do that, we actually want to row reduce A, and so I erased the row reduced matrix, but I'll put it back up. All right, and so if you remember, all solutions to the matrix equation AX equals 0 then, well, so Remember, this corresponds then to the system of equations. And so remember how we do this is we solve for x1 and x2. And then we just let x3 equal some parameter s and x4 equal some parameter t. And we get the following solution in parametric vector form. And so notice every vector that is a solution to the homogeneous equation ax equals 0 can be expressed in the following way. So this is important because this means that every vector that is in the null space of A has to be a linear combination of these two vectors. Well, so notice since each of these vectors corresponds to a different free variable in this system of equations, right? If you look at just those columns corresponding to the free variables, so the last, just those rows, the last two rows of each of these vectors, notice just by looking at these two rows, we know these vectors have to be linearly independent. So what we've just found, and stop me if this sounds like something familiar, are two vectors, so that any vector in the null space of A can be written as a linear combination of these two vectors. And these two vectors are linearly independent. So what we've actually just found is a basis for the null space of A. And so we can actually say that the null space is equal to the span of the vector -6, 5 halves, 1, 0, -5, -3 halves, 0, 1. And so these two vectors give me a basis for my null space. And we are done with the example. So null space, what do? Express the solution to ax equals 0 in parametric vector form. Take each vector that is in this expression. Those vectors together give you a basis for your null space. So we'll summarize everything we just did as a brief theorem. This is sort of a theorem in the book, but I'm adding on to it. So my added onto theorem for any m by n matrix A. One, a basis for the column space of A is always given by the pivots we'll say actually by the columns in A corresponding to pivots, or if you prefer, leading ones, in the RREF of A. And so remember, this means to find a basis for the column space, you row reduce, ask what columns do I have leading ones in. Those are, and so be very careful here. You row reduce. In the row reduced echelon form, you find the leading ones, and then you take those columns in the original matrix A. And so too, a basis for the null space of A is given by the vectors corresponding to the free variables in the parametric vector form solution to AX equals 0. And so what you can do, if you're asked to find bases for both of these, which often you will be, row reduce A, find the pivots, go back to A. Those columns in A correspond to a basis for the column space of A. Then take that same row reduced matrix, use it to express the solution to this equation in parametric vector form. Those vectors that you get are your basis for the null space. So that wraps up section 4.3, and next we'll move into 4.4.